first of all, I would like to thanks for this opportunity uh, to IIT Madras. So I am Ajit, and I am working as a postdoctoral research fellow at the Deakin University under the supervision of Professor Maria Forse. So mainly my work is on the development of battery. So this talk is on room temperature sodium sulfur battery. Yeah. So this is the slide that represents my expertise. So mostly, as I said, I have done PhD from IIT Bombay and Monash University, and I have done the PhD on sodium sulfur battery. So this is one of the piece of the work. So my expertise is on the development of current collector, electrode, and electrolyte interface for next generation rechargeable batteries. Electrolyte, mainly ionic liquid based electrolyte formulation for sodium and lithium sulfur batteries, and cathode design for high utilization of active material for sodium and lithium sulfur battery. And same time, I am utilizing the Australian synchrotron facility for in situ characterization, where I am doing the in situ surface characterization for next generation lithium metal batteries and anode free batteries. And the same time, I am working for anode free metal battery. So this is the another like the model of the battery which can promises the maximum energy density by using the any materials. So this is the motivation behind the battery, why the battery required to develop. So we can see lots of applications either in the portable or for the household. So the options we have is sulfur. Sulfur is one of the best suitable cathode for the high energy applications, because 1 gram of sulfur can store almost 5 or 6 times more energy than the existing lithium ion battery. And for sulfur also, either we have the choice for a lithium sulfur battery or sodium sulfur battery. So for the economic perspective, for the low cost energy storage, sodium sulfur is the best solution. So this is the working principle, where sodium metal is acting as a anode and sulfur cathode. So after manufacturing this cell, this is in the fully charged state. So when the cell discharge, then the sodium will come to sulfur and that convert into Na2S, and during charge again that will reverse back. So this is basically the sodiation and desodiation of sulfur cathode. Now there are several challenges that is associated with the development of sodium sulfur battery or even lithium sulfur battery. So here we can see these are the challenges, like the insulating active materials. So this is the challenges for most of the cathode materials, either in lithium or sodium. But with sulfur, this is little higher, because sulfur is insulating in nature. Neither it is conducting for sodium or lithium ion nor for electrons. So for battery, any electrode materials that is active material that require to be electronic as well as ionic conductor. So this is one of the challenge. Then the self-discharge and sluggish kinetics. This is because of the rate of reaction during charge and discharge. So that decides the kinetics of the battery, means how fast the battery can be charged and discharged. That depends on the rate of reactions. Then the volume expansion, like once the sulfur will get sodiated, there is a huge volume expansion around 150%. And the biggest challenge for both lithium sulfur or sodium sulfur is dissolution of polysulfides. So what happens when the sulfur reacts with sodium, then there are multiple intermediates that forms, and those intermediates are soluble in electrolyte. Generally in battery, active material is not supposed to be dissolved into the electrolyte, because the demerits is those intermediates can come in contact with the sodium metal, and the sodium surface can be blocked by the byproduct of those dissolved polysulfide. So this is one of the major challenge, where the engineering and the design of battery required in terms of the electrolyte which require or cathode structure. So all are moving around the dissolution of polysulfides, means the cell which can suppress the polysulfide dissolution, that can perform better in terms of long-term cycle stability or in terms of energy storage capacity. And subtle phenomena, so like as I said, these dissolved polysulfides can settle between anode and cathode, And there is a huge story behind that, right? What happens, and the whole cell life, I can say, depends upon that. So in this limited time, I don't want to. So here, uh, this work has mainly focused on the design of cathode for sodium sulfur battery. So what I have done is, like we have used the carbon cloth as a current collector, and this carbon cloth we can see badly corroded, or we can see the lots of pits has been formed, and that is deep inside the carbon fibers and the catholite. So it's like Na2SX that has been loaded on top of that, and the same time this is covered with the indium tin oxide, that is the nanoparticles on throughout the carbon surface. So like here we can see in the bigger picture, like these are the carbon fibers. Basically this is the carbon cloth, and we can see the surface of carbon, and these are the particles. Those are indium tin oxide particles. So, and finally this is covered with the active material. So this this current collector means activated carbon cloth decorated with indium tin oxide particles act as a substrate as well as current collector for the sulfur. So like here, what we have done is we have used the electron spin resonance spectra. So like in figure B, we can see, as I said, the polysulfide is dissolving into the electrolyte. So this is merit as well as demerits. So what happened is the Na2S6 or Na2 acid that get disproportionate in the electrolyte, and that makes some radical anions, that is called S3 minus radical anion. That's why this material is active in the electron spin resonance spectra. So we can see the different composition of catholite which is active. The same time, after activation, the carbon cloth is also ESR active, and the indium tin oxide particles that I am using, this is also ESR active. So it's a kind of interaction between the material which has the unpaired electrons, basically in both, in carbon as well as in indium tin oxide, and in sulfur also, because that is also radical. So for like to improve the kinetics, we need some kind of catalytic substrate that can accelerate the charge and discharge of the active material on the cathode. So here, this is the overall mechanism that we have proposed and published. So like here we can see the elemental sulfur. So basically this is showing when the sulfur get sodiated, means the battery start discharging, then what are the intermediates that forms in the cathode. So like around 2.27 volt, the Na2S8 will form, then this will take more sodium and Na2S6. And here what happened, this Na2S6 get disproportionation reaction, and this decompose, this splits into Na2S3 minus radical. So actually our current collector targeted this. So like as I said, the major disadvantage or challenges associated with this chemistry is polysulfide dissolution. So because of the interaction between the current collector and this species, we are getting one extra third peak that I will show in the electrochemical performance. So basically this current collector helps to convert the soluble product, that was the challenge for sodium sulfur battery, into the insoluble products, and the same time the indium tin oxide that has that is the nanoparticles. So that helps to nucleate the Na2S2 and Na2S. So those intermediates are well known for sluggish kinetics, as well as like in cathode, if those particles becomes bigger, like if the rate of nucleation will be less, then of course the particle size will be bigger. So the indium tin oxide is helping to increase the number of nucleating sites for those particles. So that will control the particle size smaller, and in that way means we can get the performance at even at higher current rate. So like same time, so this S3 minus radical. Okay. So this S3 minus radical was not so easy to detect in the in situ mode. So what I have done is in Raman spectroscopy, we have designed the cell where we can charge and discharge, and at the same time we can scan it. So we have a scan, and here we can see the changes in the spectra, which reveal several things like the polysulfides forming. And this was the overall electrochemical performance, which is very good with the different current rate and the enough loading of sulfur with 3.4 milligram. And the good thing with this cell structure was this cell was even working at minus 10 degrees Celsius. Of course, the chemistry and like the voltage profile has been changed, but still this was working. And so these are the summary and conclusion of this talk. I would like to thank my PhD supervisors, Professor Maria Forsyth and Professor Douglas McFarlane from Australia, Professor Sagar Mitra from IIT Bombay, and I would like to acknowledge the ARC, Store Energy LIS industry partner, and my IFM colleagues. That's it.